Hi, Algebra 2. This is Unit 13, Lesson 5. It's our last lesson for the year. So this lesson is about sample means, margins of error, and confidence intervals. So it's a couple pages, but more so because I have a lot of examples to show you. So sampling variability. What makes learning from sample data a challenge is that different samples from the same population give different results. For example, if you average all the numbers from 1 to 99, you would get 50. However, if you sample just 10 randomly chosen numbers from 1 to 99 and then find the average of just those 10 numbers, you might not get an average or a mean of 50. So the table that I have here are 8 samples, each picking 10 randomly numbers from 1 to 99, and we can see what their mean is. So if we look, all right, so sample 1, these are the numbers, so these are the 10 numbers that I picked. There's the mean. All right, it's kind of close. Sample 2, these are the 10 numbers I picked. There's the mean. Sample 3, here are the 10 numbers that I randomly picked. That's the mean. So across the bottom are all my means. You can see all of these means. They range. I got my lowest one here is 40. My highest one is 54. Okay, they range, but they're all sort of close to 50. So the value of the sample mean varies from sample to sample. Although the values in each sample differ, their means are clustered close to the actual mean of 50. What do you think will happen to the sampling mean if we increase the sample size? Well, if we increase the sample size, the bigger the sample, the closer you're going to get to the actual mean. Now, some of these were kind of close. That was just by luck. But the bigger the sample size, because 10's not a very big, the bigger the sample, the closer you get the closer you will be to the actual mean. If I had only picked 5 as my sample size, I probably would have had means that were further away from 50. Some might have been close. All right, if I only had 2 as my sample size, the probability of getting a mean, close to 50 is going to go down. So the bigger the sample size, the closer you will be to the actual mean. To help answer the question, we are going to look at a coin tossing application. The number of coin tosses will be 50 per sample, and you're going to toss 50 coins n number of times. Then record the mean and standard deviation. We'll then increase the number of repetitions to try to see what happens to the spread of the data and the measure of the mean and the standard deviation. So I'm going to take a coin and toss it 50 times, and I'm going to do that n number of times. So let's look at the first one. So the first one that I do, did 20 trials of tossing a coin 50 times. All right, and you can see my mean. I'll zoom in a little bit. My mean is 25.450. All right, and because remember, there's 50 times that I'm doing this. And my standard deviation is 3.873. All right. Now, when I increase that to 40 trials over here, all right, my mean is 25.250. Look at my standard deviation. My standard deviation is actually going down a little bit. All right, so I have fewer of those outliers. If I have 60 trials of tossing a coin 50 times, now look at my standard deviation and look at my mean. All right, but my standard deviation is going down. And look at this last time. I have 80 trials. Look at this. This is like kind of almost that normal distribution that I would expect to see. So the more trials that I have, it tends to follow that normal distribution. So as the sample size increases, the sample means tends to follow a normal distribution. As the sample size increases, the sample means get closer to the true mean. As the sample size increases, the standard deviation gets smaller, and that's a good thing because the standard deviation is how far away from the mean that I am. Now, the margin of error, that's an interval from the expected proportion that is likely to contain the majority of the data. It's basically how accurate we think our sample is relative to the population. How accurate we think our sample is relative to the population. And there is a formula for margin of error. In statistics, though, it's understood that if a data value is more than 2 standard deviations away from the mean, that the data value is unusual. So that 2 standard deviations, or 95%, is what's accepted in statistics. In a normal distribution, how much of the data falls within 2 standard deviations? I mean, the number is 95.4%, but in a lot of questions, you're just going to see them say 95%. Okay, so that's considered to be acceptable. Here's my formula for margin of error. Look at that z I have going on. It's a z-score times the square root p. P is that proportion or percent as a decimal, times 1 minus p, that percent as a decimal, divided by n. N is my sample size. So now you can look at the 95% confidence level, if you are looking at a table, is equivalent to a z-score of 1.96, all right? But you're going to see a lot of times we can actually just round that off to a z-score of 2. Why? Because it's acceptable that I'm 2 standard deviations from the mean, that 95%. So you'll see us just use 2. All right, confidence interval is the range of values that we're fairly sure our true value lies in. All right, that should be lies in, not likes, lies in. We then use the margin of error to create a confidence interval. So the confidence interval is the range of values that we are sure our true value lies in. And I'll give you an example so this makes sense. That we are sure our true value lies in. Just so you can see a picture. So we have like our estimate right here in the middle. We have our margin of error to the left and to the right. And the confidence interval is that whole thing, the range of values that we are sure our true value lies in. Okay, so here's an example. A recent poll found that 36% of all respondents would vote for candidate A in an election. The poll reported a margin of error of 4%. Now that's 4% above and below. Give an interpretation of what this margin of error means in terms of the 36% support for candidate A. So basically, if you take 36 plus 4, well, that's 40%, and 36 minus 4, okay, because that was our margin of error, 4%, is 32%. We are confident that the true percentage of people who will vote for candidate A is going to be within 4 percentage points of 36 on either side. So it's not likely to be outside of 32% to 40%. Our confidence interval is between 32 to 40%. So we are confident that our true value lies there. So we have the poll, but there's a margin of error on each side of that poll. So that's where our true value should lie between 32 to 40%. All right. At the beginning of the school year, the district implemented a new physical fitness program. A student project involves monitoring how long it takes 10th graders to run a mile. A random sample of 20 students was taken. The sample mean it currently takes 10th graders to run a mile was 7.9 minutes. The students doing the project collected 50 random samples of 10 students each and calculated the sample means. The standard deviation of their distribution of 50 sample means was 0.6 minutes. Based on this standard deviation, what is the margin of error for their sample mean estimate? The margin of error accepted is 2 standard deviations. So it's 2 times whatever the standard deviation is. That's accepted. It's an acceptable rate. So 2, and my standard deviation was 0.6. 2 times 0.6 is 1.2. So that's my margin of error, 1.2. Interpret the margin of error you found in the context of this problem. So an acceptable range would be the mean plus 1.2, which is 9.1, and the mean minus 1.2, which is 6.7. So I'm 95% confident, 95% confidence level, students will run and their score will be, their time will be between 6.7 and 9.1 minutes. Okay, so I'm confident that that will be their time. All right, I just have a few more to try. One of these is a Regents question on the back. An ecologist wants to know what percent of the 10,000 fish in a lake are cod. She takes 500 samples of size 50. The average for all these samples is 0.24 with a standard deviation of 0.06. Using this data with a 95% confidence interval, because that's what is acceptable, we can determine the percent of the fish in the lake what percent of the fish in the lake are actually going to be cod. So I'm going to take my mean plus 2 times the standard deviation, and I'm going to take my mean and I'm going to subtract 2 times the standard deviation. So that gives me 0.36 and 0.12. So I'm 95% confident that that is the percentage of cod in the lake. Anne has a coin. The Regents likes to do coin problems. She does not know if it's a fair coin. She flips the coin 100 times and obtained 73 heads and 27 tails. She ran a computer simulation of 200 samples of 100 fair coin flips. The output of the proportion of heads is shown below. So you can see that I have my samples 200. This is my mean, 0.497. This is my standard deviation. So I want to know, is the coin fair? Well, the coin is fair if it falls within 2 standard deviations of that mean. So I'm going to take the mean and I'm going to add 2 times the standard deviation. So 2 times 0.05 is 0.597. And I'm going to take the mean. Oh, and that should have been a 7. Sorry, I wrote a 2 back there. 0.497, and I'm going to subtract 2 times the standard deviation, and that's 0.397. Okay, so basically 95% of the values should be between 0.397 and 0.597 based on this computer simulation. 73 is what Anne got. She got 73 out of 100 is 0.73. Well, that doesn't fall in that acceptable range. So it's not fair. The coin is not fair. It's not a fair coin. It's not in the interval of what would be considered to be acceptable. Okay, so that's a little bit different. Here's a Regents question. A study conducted in 2004 in New York City found that 212 out of 1,334 participants had hypertension. Kim ran a simulation of 100 studies based on this data. The output of the simulation is shown in the diagram below. At a 95% confidence level, the proportion of New York City residents with hypertension and the margin of error are closest to. All right, proportion. Well, that's easy. Proportion is just the number, which is 212, over the total participants, the total population. 212 divided by 1,334 is 0.16. So that's my proportion. So I'm going to get rid of the proportions that are wrong. All right. Now I want a 95% confidence level. All right, so I can figure out my margin of error. So my margin of error is my z-score times the square root p 1 minus p over n. So my z-score that I'm going to use is 2 times, now that p proportion is 0.16, 1 minus 0.16 over n, which is 1,334. Okay, so that's the formula. That has to all go in your calculator. So the square root, now you're going to have to put a parenthesis. I want everything on top in parentheses, and then I'm going to divide by 1,334. But when I do that, I get 0.02. So that's going to be choice 2. Now let me just show you something looking at the graph, all right? So my mean is, did they tell me what my mean was? I don't think they did, but if this was like a normal distribution, my mean is somewhere in here. And if you think about it, 2 standard deviations away, okay? So this is gonna, if it was 1, 2, 1, 2, so each of those standard deviations is about 0.01. So see how this is 0.01, 0.01? So now I'm 2 standard deviations away, and 2 standard deviations away would give me that 95% confidence, right? So you can sort of tell by looking at the picture that it's 0.02 and not 0.01. So if I just went 0.01, I certainly don't have 95% of the values between 0.15 and 0.17. Okay, and that's it for this lesson.